Okay, do y'all know what a force is? Do you know the definition for force? Hi. Y'all ready? It is. Yes, it is. A push or pull. A push or pull. Okay, most important thing that we have to know is this first one right here. Forces always occur in pairs. Always occur in pairs. We have a SI unit called Newton. The abbreviation is a capital N. And force is a vector quantity, so what does that mean we have to have? It has to have a direction with it. So it's going to be a number, a unit, and a direction. So how many points would those be worth? 3. Okay, we got 2 types of forces. Contact forces and non-contact forces. What do y'all think that means? Contact means we would actually like touch it, yeah, in some way. And then non-contact, you don't. So the non-contact forces, they act at a distance. Basically, there's distance between them, and the distance could be big, but they're still going to put a force on something. Can you think of one that would fall into that category? Yep, magnetism, magnetic force. Does the magnet have to touch to pull or push another magnet? Nope. So that's what we mean at a distance. What else? That actually does touch it.
Environmental forces?
Gravity. And the last one is electrical. Okay, right now we're not really going to focus very much on magnetic and electrical, but you need to know that they are a force and they act across a distance. Gravitational, we're definitely going to be using. There's these different symbols or abbreviations, because like, do you really want to write this word out every single time you have to label it? No. So we're going to write all of the symbols that go with this stuff. So it's the force of gravity. So it's a capital F with a little g. Okay, what would be some contact forces? Yeah, like you actually. So that's called the applied force.
Second lunch students, report to second lunch at this time.
Okay.
Second lunch students only.
Friction. So a frictional force. That's going to be capital F, little f. Air resistance. Which air resistance is a type of friction. Y'all know what air resistance is? What you mean? Yeah. Like, you know when you're riding in the car, you stick your arm out, and it's like, That's it. That's a big example of air resistance. Even if you just take like this sheet of paper, and that's air resistance when it falls. Okay, we have a spring force. Y'all know what a spring is, right? Tension. What's tension? Where would it be at? But where would it be at most of the time?
It'll be at the center. At the base. Basically, if you took a rubber band and stretched it up.
Well, maybe that's elastic though, but in a rope or a string is where the tension will be marked.
In the middle.
Yeah, but you're going to have these different diagrams that you're going to have to label where the force is. Tension is going to be where you see a rope.
A rope.
Yeah.
But can it be other materials too?
It can be, yes. The elastic one, I guess that is.
And isn't it based on the elasticity of the material? Because now.
Oh, how much it can hold? Yeah, but we're not going to really measure all of that. You just need to be able to identify where it is. Okay? Okay, the last thing, this is the new part that you don't know. It's called the normal force. F with a capital N. The normal force. I guess so. Okay, so do you know how or why you're able to sit in the chair? Like what's causing you to be able to sit in your chair? Okay, if gravity is the answer, listen to me. This is going to get weird. This is the weird physics stuff. Don't just follow with me. I said, how are you able to sit in your chair? And y'all all say gravity. And I agree with you because, yeah, you're not floating around, right? Okay, but if gravity is the only force, then why aren't you following through it?
Is it? It's not just gravity. It's something about weight and something else pulling.
No, like, okay, I'm standing on the ground, right?
But you want to know why we're not following through.
Well, if what's causing me to be able to stand on the ground, y'all's answer would be gravity, right? But then if it's only gravity, then why am I not pulled through it?
Like, no, is it pressure?
Mm-mm. It's called the normal force. What was the one thing at the beginning I put a star by and I said, this is the most important thing you have to know through this unit? That gravity's not the only force. Gravity's pulling you down, but something has to be pushing you up. The seat of the chair is pushing you up. Does that make sense? So the floor is pushing me up. The floor is not pushing you up right now. The floor is pushing the desk up. And then the seat of the desk. Does that make sense? Okay, so the normal force is the force exerted perpendicular to the surface of an object. Perpendicular to the surface of an object. So let's kind of break that down. These two lines would be parallel, right? But if this is the surface, the normal force is perpendicular to the surface. It comes out of the surface. Does that make sense? It comes out of the surface. another way to say this, the normal force keeps objects from going through each other. Like, you're not going to go through the seat, are you? No. Y'all are so smart. I'm serious. Y'all are gonna be like so. Y'all know so much. Okay, so let's put this in a picture. I have a box right there on the floor. Okay, what force is acting on it? Okay, gravity's pulling it down. That should be the automatic answer that we automatically give. Okay, and then the box isn't falling through the floor, so we know the normal force. Okay, so gravity acts from your center. Did y'all know that? It pulls from the center of every object. So I'm gonna do my best to give you the center. I guess that's pretty good. Gravity is a vector. Force is a vector, so there's my arrow. I'm gonna label that F, little g. Gravity's pulling down. The floor is pushing up. So that one is the normal force. And I didn't make them the same size, so I'm not that good. They should be the same size. No, the arrows, the vectors. Okay? What about the guy pushing on the wall? What forces do we have? Applied force, so he is pushing this way. F-A-P-P. And what's happening? Is he gonna fall through the wall? No. The normal force acts perpendicular, so it comes out of the surface and it pushes back. And they should be the same size. How we feel about that? Everybody okay? Okay. Now let's change our dimension a little bit. We're not up, down, left, and right. We're now slanted. Let's say the box is at rest. What force is acting on it? Gravity is pulling down. And the normal force is pushing up. But is it going to be straight up now? It has to come out of the surface, so it's at an angle. Very good, Malka. How do we feel about that? Look, your surface isn't up and down anymore. Your surface is a slant, so I tried to come out of the slant. That's it. It comes out of the surface. Cool? Yes, no? Yes. Okay. Let's add some math to it. Can you add and subtract? Then you can do this. He says no. The combination of all the forces acting on an object. The combination of all the forces acting on an object. So when things are just laying around your house, now you can actually understand how they're sitting there. What force is acting on this book? We just did it. Yeah. Gravity. Okay, so now I'm going to put some numbers with it. I'm going to say that gravity is pulling with 5 newtons of force. And the normal force is pushing up on the book with 5 newtons of force.
So it's equal, that's why it's down the same.
The net force is the total force on the book. No, they're in opposite directions. So it's 0 newtons. That's not the word on, that is the number 0 with the symbol for newtons. Okay? Okay, before I even put any numbers with this, can y'all look at those arrows and tell me if that box is going to move? It is going to move? Which way? Right or left? To the right. Everybody sees that? Okay, now watch. 4 newtons, 4 newtons. 6 newtons, 12 newtons. I want to know what is the net force on the box.
6.
Okay, it's a vector.
6 newtons, east of
6 newtons east. So, you see these two? They're just both pushing with the same amount. So these two cancel. Right? And then we have these two. Who's going to win? 12 by how much? 6 newtons east. Does that make sense? Yes or no? What would happen if this were 2? Okay, I'm not ready for y'all. You're not going to know how to actually get the number. But if I said that this number was 2, could y'all all imagine what could happen to that box? No? Okay, look. This would be 4 versus 2. Who's going to win? 4. And then you have 12 versus 6. Who's going to win? 12. So these two forces are going to move them at an angle. Does that make sense? Okay. Okay. This is me. And this is Malachi. No, I'm kidding. What is the net force on the rope? Is there anybody who's struggling to understand what we're doing here? Kind of? Who's in the middle?
I have a question. I understand if you guys subtract it, but why wouldn't you add it if the rope is handling that much force? And he's going that way, he's going that way. So it's getting that amount from each, like 200 right there and 150 right there. So why isn't it added?
Because they're in opposite directions. So every time the forces are in opposite directions, we subtract. So that's what we did over here. 4 minus 4, that's 0. 12 minus 6, that's 6. Okay, so they're not working together, are they? They're working against each other. He's going this way, he's going this way.
Yeah, but
So you subtract it.
he's pulling it more on that side. So they're like, out in my.
Oh, that doesn't matter. You're looking at this piece versus this piece.
And the
That
middle part.
that doesn't matter. That doesn't matter. Okay, last one. The net force on the, whatever that is, cart. 225 newtons west. So when the arrows are in the same direction, we add. How's that? Yes, it is very easy. Okay. This is going to combine some of our speed velocity stuff with forces. So we have something called balanced and unbalanced. Okay, my little guy right here in the skateboard. What's their motion? What do y'all think their motion is? Nothing. What do we call motion, no motion? At rest. Okay? And we're going to, how is he able to stand here at rest? Because gravity is pulling down and the normal force is pushing up. So that's the same thing on the skateboard, right? Okay? And those two are equal, right? So are they balanced or unbalanced? That's called balanced forces. Because they're equal and opposite. Okay? Now, he wants to actually take off. So he puts his foot on the ground and he pushes on the ground with 100 newtons of force. But right here at this tire, there's a little rock. And that little rock is saying, I'm going to push with 100 newtons of force. What would we label that type of force right there for the rock? Yeah, it's from the other side. Which one? What is that rock going to give me? No, he's applying. He's pushed. Huh? No, there's no string or rope. There's no spring. I heard it. Friction. What's his motion going to be? What do we call that motion? At rest. What kind of forces do I have? Balanced. And what would be his net force? 0 newtons. So he decides he's going to push even harder. Now he's going to push with 120 newtons of force. Yeah, he applied that. You're right. I'm sorry, I forgot to write it. We still have our little rock there. And how much is that rock giving us? 100 newtons of friction. What's his motion going to be? No, what's his motion going to be? So these are, when I ask you for his motion, that's going to be words that I taught you last week. Last unit, last stuff. What's his motion going to be? Is he going to be at rest? What's he going to do? There it is. Acceleration. Are my forces balanced or unbalanced? Unbalanced. And the net force is 20 newtons east. So what did he have to do so that acceleration could happen? He had to push harder. Okay, so here is the rule. You must overcome friction for an object to accelerate. You must overcome friction for an object to accelerate. So, everybody take your hand, put it on the desk. Now just barely push forward. Yeah, I said barely though. You're given a force, aren't you? But you're equal to the friction that's between the desk and the hand. You have to have a force greater. Now push a little harder. Push a little harder till your hand can actually accelerate. Once your hand accelerates, then you have overcome the friction that was holding it in place. Does that make sense? So that's for anything to move. The first thing that has to happen is you have to have a force that's greater than the friction holding it there. Okay? Okay, last one. He's on his board now. He already pushed off and he's just coasting forward. We got 50 newtons of air resistance, and we've got 50 newtons of friction. What is his motion? No, what did I say he was doing?
I don't think he's moving anymore because the wind blowing him that way. And it's like those two are equal now. That's like the opposing part. And if he's 100 trying to go, it's equal. So he can't move anymore.
I said he was on that board and he was just chilling, he was just coasting.
So he stopped.
Not yet. He's at a constant speed in a straight line. So that's not acceleration, is it? No. What are your forces on here? Look at your numbers. What are they? I know, I said look at the numbers. Are we balanced or unbalanced? We're balanced. And what's the net force? Zero newtons. balanced forces. Two forces that are equal in size but opposite in direction. Equal in size and opposite in direction. Equal in size and opposite in direction. So you can look at your pictures above. What were the two ways that we got balanced forces? What was our motion at the top? At rest, and then what was the last one? That's the two things that you get from balanced forces. So, we either stay at rest, or we move at a constant speed in a straight line. Unbalanced forces are two forces not equal in size, and it can be the same or opposite directions. Because this is how you get acceleration. They always cause a change in motion. And a change in motion means acceleration. That can be positive or negative. What are the three ways we learn that we accelerate? What are the three ways we accelerate? Change direction, speed up, or slow down. Those three things, unbalanced forces cause speed up, slow down, or change direction. Because that is what acceleration means. Those are the three things for acceleration. Okay? Can y'all say the last word? Equilibrium. Just a fancy word that they like to use sometimes, so I give you the definitions, they know what they're talking about. Equilibrium is basically like balanced. Okay? So it's a state of motion in which opposing forces are balanced. Any questions?